we were typically talking about position vectors, right? So we've got some vector function like this, which is, I don't know, right? That would be an example of a vector function. So we got an input parameter, which is t, and you give it a certain value of t, and the function gives you a vector out, okay? And we typically used vector functions are often for what we call a position function, where again, remember a position function RT always starts at the origin of our coordinate system, and it points to some point like that, right, for a particular value of t. At some t, other value of t, maybe it looks like this. At another value of t, maybe it looks like that. Okay, different values of t. Ooh, that's a crooked vector. And we use it to define a curve in 3D space. So you put in a different value of t, and r points to a different point on that curve. Okay, and we said that with these vector functions, we can do calculus to them just like we can with scalar functions, which means we can take their derivatives, which means we can take their integrals. It's no big deal. It's just a little bit more work. All you do is, you know, to take the integral of, or take the derivative of r of t with respect to that parameter t, you just take the derivatives of each component. And similarly for integrals, we can take the integral of that vector function with respect to t. It's just going to be the integrals of each component added up. Pardon me, that's not right. In a vector. And then we looked at some special vectors, the tangent vector and the normal vector, okay? And today we'll do a quick example just to flex our differentiation muscles a bit, remind ourselves how to do differentiation of a little bit more complex thing. So if we have a vector function r of t, which is equal to t squared I hat plus 3t j hat plus 5k hat, and we want to find the unit tangent vector and the unit normal vector. And we said last day that the tangent vector is simply the derivative of the position vector. Okay, so our tangent vector is simply the derivative of our position vector. Because if you take the derivative of position, you get velocity. And velocity we know is tangent to the trajectory. Okay. So that's pretty easy. You just take the derivative with respect to t of each component of your position vector. So we're going to end up with 2t I hat plus 3j hat. And that'll be it, right? Because the third one is 0k hat. Okay, so that's our tangent vector. That's easy. We need the unit tangent vector, which means we take that and we divide it by its magnitude. That's too much writing. We take the tangent vector and we divide it by its magnitude. So 2 squared plus 3 squared, 4 plus 9 is 13, 1 over root 13. Oh my goodness. It's obviously Monday morning, isn't it? That's not right either. Let's slow down. So we got to take this squared plus this squared plus this squared. So obviously I forgot the t, right? So it would be 4t squared plus 9 square root. 4t squared plus 9 square root. Okay, that would be the magnitude. So we divide the tangent vector by its magnitude. Now we have the unit tangent vector. Okay, well now to find the normal vector, we take the derivative of the unit tangent vector. Not the tangent vector, but the unit tangent vector. To get the normal vector, you have to take the derivative of the unit tangent vector. So we want to take the derivative of the unit tangent vector with respect to t. Did I make another mistake? Wow. I forgot this t here. Obviously here, right, we've got a 2t, so I have to write 2t there. Okay, so the derivative of the unit tangent vector, we take the derivative of each of the two components. There's only an x and a y component, the z component 0, so we can forget about that. So we're going to take the derivative of 2t over 4t squared plus 9 square root. Okay, we're going to take the derivative with respect to t of that, I hat, plus the derivative of 3 over 4t squared plus 9 square root, the derivative of that j hat. Okay, so if we look at the first one, we've got a function of t over another function of t, and we're taking the derivative, so we have to use the quotient rule, right? So I'm going to do this one first. So the quotient rule is bottom times the derivative of the top. So the bottom times the derivative of the top minus the top times the derivative of the bottom, which would be 1/2 4t squared plus 9, and the derivative of what's inside, 2 times 4 is 8t, all over the bottom squared. Okay? Let me know if I make any mistakes. I've already made 3, so. 2 4t squared plus 9 minus 1/2 2t times 8t, yep, 1/2 4t minus 1/2, because we're taking the derivative of something to the 1/2. Okay, so that's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. I think I got it right now. Which is going to be equal, if we do some simplification, okay, so that's the the derivative of the x component. So that'll be the x component of our derivative. Okay, now we'll take the derivative of this y component here. A little bit easier because the top is no longer a function of t, but I'll still use the quotient rule. The bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, all over the bottom squared. I'm just going to write the end result. It's just a little bit of simplification. We end up with that. The bottom times the derivative of the top minus the top times the derivative of the bottom, which would be 1/2 4t squared plus 9 1/2 8t all over the bottom squared. Right. Okay. So now we've got the two components of our derivative. So the derivative of our unit tangent vector with respect to t All right, is this getting boring yet? This is just review from last year, right? It's all the same, it's just, in this case, twice as much work, because we got two terms. Okay, well, taking the derivative of the unit tangent vector gives me the normal vector, okay? I want the unit normal vector, which means I have to take this result and divide it by its magnitude, and then I got the unit normal vector. This itself is just the normal vector, which may not be a unit vector. If we want to make sure this is a unit vector, we divide it by its magnitude, okay? So if we find the magnitude of this derivative, right? It's just this squared plus this squared times this. This squared plus this squared square root times this. Okay, so now we take our derivative of the unit tangent vector, which gives us the normal vector, and we divide it by its magnitude. And that gives us the unit normal vector. Right, so that's the derivative of the unit tangent vector divided by the magnitude of the derivative of the unit tangent vector. So we get that, okay? So the only tricky part is you gotta, right, keep your wits about you when you're doing the derivatives or the integrals, recognizing there's nothing different with vector functions other than you're taking multiple derivatives or multiple integrals. With respect to tangent vectors and unit tangent vectors, derivative of the position vector gives you the tangent vector. You then got to divide it by its magnitude, and you got the unit tangent vector. You take the derivative of the unit tangent vector, you get the normal vector. You divide it by its magnitude, you got the unit normal vector. Okay, that's all there is to it. Okay, and then, you could ask, well, what are these vectors, say, for a parameter t value equal to 0? Well, in that case, your unit tangent vector, when t is equal to 0, you would get 1/3, 0, 3, which would simply be j hat. And your unit normal vector, when t is equal to 0, would be 1/9 plus 4t squared square root 3 minus 2t when t is equal to 0 is going to simply give you I hat, right? Because the y component is going to be 0 when t is equal to 0. This t is also equal to 0, so we end up with 1 over 3 times 3 I hat. You just get I hat. Okay, any questions about unit tangent vector, unit normal vector? Most common error is people get the unit tangent vector and they take the derivative and they think they got the unit normal vector and they stop, right? You take the derivative of the unit tangent vector, you get the normal vector. You have to divide it by its magnitude then to get the unit normal vector. Don't forget that step. All right, so that's it for vector functions. Now we know what those are. Let's move on and let's look at a new concept called arc length and a new type of integral called a scalar line integral. Once we have multivariable calculus, we can do a lot more interesting things, okay? So first, arc length. We talked a little bit about arc length already. If we would have some curve in three-dimensional space, I don't know, it looks something like this. Okay, we've got some curve in three-dimensional space. The arc length from one point to another, let's say from this point here, point P1, to this point here called P2. If we want to find the arc length, we're looking for this distance. Okay, it's the distance that the odometer in your car would register or measure as you drive from point P1 to point P2 along that curve. Okay, it is not this distance. Okay, that red line is a straight line between P1 and P2. That's the distance as the crow flies, right? That is not arc length. Arc length is the actual distance along the curve, traveled along the curve. Okay, well, how can we calculate that? Well, like we always do in calculus, we take a big problem, we divide it into smaller problems. So what we could do is we could take this curve. If it was a straight line, it would be no big deal, right? If you have the coordinates of the starting point and end point, everybody knows how to find the distance between 2 points, right? Whether it's in two-dimensional or three-dimensional, no big deal. But as soon as we have a curve, it gets more complicated. So what do? We say, okay, we're going to take that curve and we're going to divide it into really small segments where the segments are so small they can approximate a straight line each. Each one of those little segments is about a straight line if we make this segment small enough, right? So we find the length of one of these small straight line segments, we add it to the next one, to the next one, to the next one, and we get the overall arc length, okay? Well, we're going to use position vectors to do this. We're going to say, well, let's say we're going to, this is nowhere near small enough a segment, but let's say we're going to divide the curve up and we're going to look at this segment from here to here. And we're going to say that little black line is almost the same length as the blue line between those 2 points, okay? The closer those 2 points get together, of course, the better that approximation is. But for illustrative purposes, so you can see it, we're going to say that black line is about the same length as the blue line between those 2 points, okay? Well, let's call this point A, let's call this point B. We can draw a position vector for that point. We can draw a position vector for that point, okay? Call this one over here R when time is such that we're at point A. Call this one here R for a value of t such that we're at point B, okay? And then we can make this line between A and B, we can make it a vector too. Okay, and I'm going to call that vector delta R, because delta R, let's do it down here. Delta R, that vector, that small vector, is equal to RTB minus RTA, right? It's just vector addition. Okay, well, we're going to use the magnitude of that short vector to approximate the arc length between points A and B. If A and B are close enough, then the magnitude of that vector delta r is about equal to the arc length along the curve from A to B, if those 2 points are close enough. Okay, let's call that arc length delta S. Okay, so delta S is approximately equal to the magnitude of this delta r, which is equal to the magnitude of RTB minus RTA. Okay, with me so far? It's just an approximation. Okay, so this, we're just going to say it's equal to delta r. Okay, it's the magnitude of this vector delta r. We're going to write that magnitude a little bit different. If I take a vector, the vector delta r, and I dot it with itself, what do I get? I get the magnitude of that vector squared, right? And if that's supposed to be equal to the magnitude, well, then I got to take the square root of that, and I'll get the magnitude. So that's equal to that. Okay? Dot product of a vector with itself, it's its magnitude squared. Take the square root, you got the magnitude of the vector. Okay, now I'm going to multiply that by delta t over delta t, where delta t is equal to tb minus ta. Okay, it's the value of t when we're at point B on the curve minus the value of t for when we're at point A on the curve. That's delta t. And if I multiply that by delta t over delta t, that's multiplying by 1. That's legit, right? I haven't changed the equation. Now I'm going to take this delta t inside the square root, which means I got 2 of them. So I end up with delta r over delta t dot delta r over delta t. And I still have the 1 on top outside. Okay, so just like we did back in first year, in the limit, as we make those 2 points A and B really close, or as delta r gets very, very, very small, the delta turns into what? What did we do last year? The delta turns into a d, right? A differential. Sorry. As delta goes to 0, delta becomes a d. Okay, so now we can write that instead of delta s, we have ds is equal to, instead of delta r over delta t, we got dr by dt dot dr by dt dt. So what we've done is we've found an expression for ds, where ds is this, I'll go back down in a second, ds is this red arc length, okay, as A and B get really close together. ds is this small arc length. We've written the small arc length in terms of some number times dt, where dt is the difference in the parameter t between point A and point B. Okay? Now we're looking for the total arc length of this curve from point P1 to point P2. So what do? Well, we add up all the ds's. For every little segment along that curve, we can find the ds. We add up all the ds's, we got the total arc length from point P1 to point P2. So our total arc length from point P1 to point P2, right? That was the whole curve. all the way from here, all the way to here. We're finding this total arc length. We're just adding up all these little ds's. And to add up differentials, we use an integral, right? So S is going to be the integral of all these ds's, where the ds is equal to the square root of r prime, the derivative, dot r prime dt. Okay, and t is going to go from what to what? Well, I don't think I wrote anything down up here on the curve. Let's say that r of t points here when t is equal to t1, so point 1. Here, t is equal to t2. Okay? So our position vector points like that when t is equal to t1, and it points like that when t is equal to t2. So t is going to go from t1 to t2. Okay? So our position vector, which we start with, is a function of t. Okay? We want to find the arc length from one point to another along the curve that is defined by that position vector. We can take the integral of, all we have to do is take the integral of this as t varies from t1 to t2. Okay, and we know everything on the right-hand side of that equation. Presumably, we know what the position vector is, and we know what t is to be at one point, and what t is for the second point. And we can find now the arc length between those 2 points along the curve. Okay? And that's all there is to it. That's how we find arc length of a curve that's defined by a particular position vector. Okay, now our position vector itself is going to be some function x of t, y of t, z of t, right? Some expressions, all functions of t. X, y, and z just means the x, y, and z components of that position vector. So that means this dot product of the derivative with itself is just going to be dx by dt squared plus dy by dt squared. Ugh, that's messy. Dy by dt squared plus dz by dt squared. So another way we can write an equation that finds the arc length between 2 points on a curve. Again, we are integrating with respect to t, so our limits are values of t. And it's just the square root of that. Okay, so that's another way you sometimes see it. So that's arc length. We find the integral of something dt. And that something is the square root of the dot product of the position vector of the curve with respect to itself. All right, so let's look at an example or two. So we're given this position vector. Where t goes from 0 to pi. And we want to find the arc length of the curve that's defined by that position vector as t goes from 0 to pi. What kind of curve would that be? It's a circle, right? Centered at the origin. What would be the radius of that circle? What would be the radius of the circle? Any idea? Well, just look at when t is equal to 0, what do you get for the x and y components? When t is equal to 0. The x component of that position vector is, careful, when t is equal to 0, you got the cos of 0, which is 1, right? When t is equal to 0, sine 2t is 0, right? So when t is equal to 0, that position vector points at the coordinates 1, 0, right? When t is equal to pi by 2, cos of pi by 2 is, well, careful, t is equal to pi by 2. 2 times pi by 2 would be what? Pi, cos of pi is? You got it. If you don't know these values, you're going to run into cos and sine for the next 2 years, right? So the radius would be 1, right? Because any coordinates or any values of t you put in there, the maximum value you're going to get for x or y is 1, right? Right? Because there's no, the coefficients of these cos and sine is 1, right? And remember, a cos or a sine function gives you a max value of 1. So if you multiply it by 1, then, well, the radius is 1, okay? Okay, but that's not what we were asked. We were asked to find the arc length. So we're finding basically the distance around this circle as t goes from 0 to pi. Okay, how many times is that around the circle? Or does it go around the circle the whole time? First half? Right? So when t is going to 0, the argument of our cos function is 0. When t goes to pi, we go to 2 pi. Would that not be all the way around the circle? Right? Okay, I'm just trying to get you. We're going to run in, at least in this course, you're going to run into cos and sine over and over and over again, right? So if you don't have this memorized, right, that's cos, and that's sine. Oh, sorry, I'm a bad artist, right? Make sure you do that. Okay, so it's a circle, and we're basically finding the circumference of the circle, but we're going to use the arc length formula to do it. Well, we need the derivative of our position vector, right? So the derivative of cos is negative sine times the derivative of what's inside. Derivative of sine is cos times what's inside. Okay, so if I take the dot product of that, what do I get? Well, I get 4 sine squared 2t plus 4 cos squared 2t, 2t, which is equal to what? It's just equal to 4, right? Because sine squared plus cos squared is equal to 1. So you take the 4 common factor out. 4 times 1 is 4. Okay, so our dot product is 4. So our total arc length is the derivative as t goes from 0 to pi, because we were told that up here, right? The square root of the dot product of the position vector with itself, dt. We get 2 pi. Now, a very handy thing you can do is you can say, well, what if I just want to go from 0 to some arbitrary value of t? Instead of t going from 0 to pi, what if I change my integral from, oh, pardon me, don't do that. Sorry. I can come up with a function for my arc length s as a function of t if I do this, right? From 0, instead of 0 to pi, I go from 0 to some arbitrary value of t. Same thing, root 4 dt, right? I get 2t. Plug in a value for t, I got the arc length around that particular circle for that value of t. Okay, so this gives us a parameterization of our circle. For the circle, it's pretty easy to get. For arbitrary curves, it's usually not that easy. Okay, another quick example. We're trying to find the arc length of a glider that is traveling along a helix, right? Yeah. Right, that position vector would give us a helix. If you look at the x and y components, again, they're a cos and a sine. So in the xy plane, it's a circle. If you look at the z component, it's just a function of t. So as t increases, you go around in a circle in the xy component, and you go up in z. So this gives us that helix we saw a couple of lectures back, okay? So again, it always helps if you can visualize the curve that you're dealing with, given its position vector. Okay, we want to find this as t goes from 0 to 2 pi. Well, again, you take the derivative of your position vector. Derivative of cos is negative sine t I hat plus cos t j hat plus derivative of t is 1, so that's just k hat. I'm just going to jump back and forth between notation because I favor the angle brackets, but I find Dr. Chow, who teaches the other section, he likes ijk for some reason. And so if he writes a midterm problem with ijk, I don't want you to be spooked by that. I want you to have seen it. So every once in a while, I'm going to try to write it that way too. Okay, so now my arc length is going to be equal to the derivative as t goes from 0 to 2 pi of the square root of r prime dot r prime. So the square root of r prime dot r prime is going to be sine squared t plus cos squared t plus 1 square root dt. Well, sine squared plus cos squared of anything is equal to 1. So I got root 2 dt. So I get 2 pi root 2. Okay? So that's arc length. So we got a pretty simple equation for arc length. Square root of r prime dot r prime dt. Okay, any questions about that? Okay, couple of things we can say. We can think of arc length, obviously, as the displacement along a curve. So if we take the derivative of arc length, what do we get? The derivative of displacement is, okay, now careful, you're partially right. Arc length, is arc length a scalar or is it a vector? Arc length. It's a scalar, right? Gives us a number. It's a distance along the curve. Okay, so arc length is a scalar. So if we take the derivative of a scalar, we get another scalar. So what is the scalar related to velocity? What do we call it? Speed, exactly. Right? This is equal to the magnitude of velocity, which is equal to speed. Okay, and we talked about the tangent vector. The tangent vector of that curve would be equal to the derivative of the position vector with respect to t. That gives us our velocity, which means that if we take the unit tangent vector, it's the velocity divided by its magnitude, right? Okay, well, if velocity is dr by dt, and the magnitude of velocity is speed, and we said speed is ds by dt, then the unit tangent vector is dr by ds. Okay, so if you can express your position vector in terms of s, you find its derivative, you've got the unit tangent vector. Okay. All right, so that's arc length. Okay, so it's a relatively simple integral formula that you can use to calculate the arc length along a curve, if you have its position vector. All right, let's move to the second topic, which is kind of related, and that is a line integral. Well, a scalar line integral. So what's the difference between an engineering student and a management student? Have you heard this one? Any management students here? I should ask that first. Well, I can say that because my son went through management, so I can poke fun at them. What's the difference between a management student and an engineering student? A management student can only take integrals in the x direction, but engineers can take it in any direction. Okay, and that's what we're going to do now. Last year when you did integration, you did stuff like this. You were given a function, y is equal to some function of x, right? And you found the derivative, the integral of that function dx, right? That's all you did last year in the second math course, right? And you learned all the different techniques for taking those integrals. Well, you never thought about it back then, but you were taking the integration in a specific direction, in the x direction. That's what dx means, right? You're taking the integral in that direction. Okay? Now, in a two-dimensional function, there's really only two directions we're typically interested in taking a derivative. In the x direction, you could also take it in the y direction, okay, which you never did back then. We typically line it up this way, and we take the integral in the x direction. Okay, well that's boring because life is in 3 dimensions and a lot of the functions we deal with are in 3 dimensions. And sometimes you need to take the derivative or the integral. The same is true for differentiation, as we'll see in a little bit. We don't necessarily want to take it in one direction, we want to take it in some arbitrary direction. Okay? And that's what we're going to learn how to do in this course. We're going to learn how to take derivatives and integrals in any direction in 3-dimensional space, which makes us a lot more useful than management students, right? I didn't get a whole lot of laughs, whatever. Just wait till I start talking about you civil engineering students. Then you'll start throwing fruit, right? You know the difference, but no, I won't start. I'll wait till I have a better rapport with you before I start insulting some of you to your face. I had a first when I was in first year. When I went through engineering, we had to take a ton of humanities electives, and we took them in first year and second year and third year. And first year I took a philosophy course, and our philosophy professor, he said, when I insult you because you're a Jew or a Christian or a Muslim, or because you're black or white, or because you're a male or a female, or whatever, don't be offended because I'm going to get all of you at some point during the course. I'm going to offend all of you. He said it right at the beginning. So don't get all worked up when I offend you because everybody will get their turn. Not true here. I only pick on civil engineers. So, okay, line integrals. Let's talk first about something that you probably did last year. And no, I'm tempted to just go to this. I'm just going to go cut to the chase because we're running out of time anyway. So let's think now in 3 dimensions. Okay, we've got some curve in 3 dimensions like this. Basically what we want to do, there's going to be 2 things going on. There is going to be a vector function that exists in this 3-dimensional space. That's one thing that's going on. Okay? A vector function that exists in this 3-dimensional space, it's going to be something like, what notation did we use? Yeah, some function of x, y, and z. right? You put a particular three-dimensional coordinate into this function and you get a value. It might correspond to the temperature at that point in space or the pressure, who knows, right? But we've got some function. Did I call it a vector function? If I did, I misspoke. It's just a plain ordinary function of three variables. You put x, y, z in, you get a scalar value out. Okay, that's one thing we've got going on here. The other thing we got going on is a curve in 3 dimensions. Okay, these two things are separate. This three-dimensional function, f of x, y, z, exists everywhere here in three-dimensional space. You put any point in here, you get the temperature at that point, or the pressure, or whatever. Okay? The other thing we got going on is we have a specific path through three-dimensional space. We had the same thing going on last year, right, up here. You had two things going on. You had a function, and you had a path. And the path you were following was in the x direction, right? Because this is dx. Okay, well, now we're going to do something a little different, but the same. We've got some function that we want to integrate along a path. But now our path is going to be this arbitrary three-dimensional curve through space. Okay? It's not just in the positive x direction. Up here, you're integrating f of x in the positive x direction. That's all you were doing last year, right? Boring. We want to integrate some function along here. Okay, and that's what we're going to do with a scalar line integral. Okay, it's called a scalar line integral because the function is a scalar function that we're integrating and we get a scalar value out. But we're integrating, we should really call it a scalar curve integral, right? Because a line is a particular type of curve, but we call it a scalar line integral. We are integrating along this line. That's all we're doing. Okay? So we're not integrating this function in the x direction or the y direction or the z direction. We're integrating it along this particular line. And you might ask, well, why would we ever want to do that? There's lots of different applications. What I'm skipping in the lecture notes actually is finding the mass of a thin rod. Okay? Basically, you're solving a scalar line integral, but it's kind of cheating. It's like last year, you're doing it in the x direction, okay? We're generalizing it such that you can integrate any function that exists everywhere in space along a particular curve. So remember, these two things are separate. This is separate from the line you're integrating it on, or the curve you're integrating it. I could take the same function and I could integrate it along that curve, or I could integrate it along that curve. Or if I was really boring, I could integrate it along the x-axis if I wanted to, because that's a curve too. Okay, so that's all we're doing here with a scalar line integral. And I think we're going to do that on Wednesday. Okay, so we'll see you on Wednesday.